Okay, so yesterday we said whenever we're comparing two relative acids to one another and determining which one's more acidic, the simple thing to do is to write out a simple acid-base equilibrium reaction and then look at your conjugate base and ask which of the conjugate bases is more stable. And we came up with this mnemonic called cardio, where we look at the charges first, atoms second, resonance third, dipole induction after that, and then orbitals last. So in the first example, we said, all right, if we compare the conjugate base for hydronium to the conjugate base of water, water on the right-hand side doesn't have a charge, therefore it's more stable than the one with the charge. That means hydronium's a stronger acid. And then we got into atoms after that, and we said, all right, what if they both have a negative charge and we're tied in that charge category? If we're comparing two atoms that have a charge and they're in the same row, the one that's more electronegative is going to be more stable. Therefore, in this case, water is the stronger acid. With atomic size, we're comparing two atoms with the same charge that are in the same column. So in this case, iodide, is much bigger than chloride. It's more stable, which means hydroiodic acid is stronger. Then after that, we go to resonance. Conjugate bases that have resonance are a lot more stable. So in this example, the carboxylic acid's more acidic. Then we saw dipole induction. In this case, there was no resonance. Charges were on the same atom. Everything was tied. But the fluorines that were attached to the molecule on the bottom were tugging on the negative charge. That made it more stable. Then we said this really depends on proximity of the negative charges. Typically, dipole induction drops off with distance pretty dramatically. I can't remember if it's r to the fourth or something like that, but it's a big drop off. And then last but not least, we looked at orbitals. We said if you have a negative charge in an sp orbital, it's closer to the nucleus. That means it's more stable than if it were in an sp3 orbital. There are exceptions to this, though. These are just general guidelines, so I'll show you the most common exception. And I think this is one you might run into in sapling, which is why I'm bringing it up. So let's take the following example. Let's say we have ammonia, and we treat it with some sort of base. That means we're going to treat ammonia as the acid in this situation, right? Because B just stands for base. If I do that and pluck a proton off, that means that this nitrogen would then have two lone pairs, two remaining hydrogens, and a formal charge that is negative, plus our conjugate acid right there. And let's compare this to a second completely different molecule. We'll do acetylene again. And with acetylene, you can pluck off one of those protons off of one of the terminal carbons. That gives that carbon a negative charge, and we end up with our conjugate acid. All right, if we go through the cardio rules, we're comparing this conjugate base to this conjugate base. Both of them have a -1 charge, so we're tied at that charge level. Then we go down to atom. All right, which one do you think would be more stable according to the atom rule? Nitrogen, right? Nitrogen's more electronegative than carbon. Intuitively, we would think, shouldn't that one be more stable than the carbon with the negative charge? No, it's a weird exception. So if we look at this one, we'd say we would expect this to be more stable due to electronegativity. However, that's simply not true. It is more acidic. The reality is nitrogen isn't that electronegative, and in this case, orbital hybridization is more stabilizing than nitrogen having the negative charge. Like I said, the cardio rules are just general guidelines. They work about 90-ish% of the time, but there's those weird examples that might bend the rules a little bit. Does that make sense? All right. So today what we're going to do is kind of an offshoot of what we did yesterday, and we're going to focus on identifying the most acidic protons in one molecule. And the simple trick I'll show you is when in doubt, draw all possible conjugate bases. And then compare all of them. Okay, so let's do this one first. So identify the most acidic proton. And I'm going to color code them. I really like color coding these. And we'll do it this way. I'm just going to put R groups on here. Off of the left carbon up here, I'm going to have a red proton. And on the right, I'm going to have 3 blue protons. So essentially the question is, which is going to be more acidic, the red proton or the blue proton? Meaning, if I were to treat this with a base, which proton would get removed first, preferentially over the other, the red one or the blue one? So let's try this. It's always good to argue. At least in a classroom, maybe not in Washington, D.C. So we'll do minus the red proton first. And draw the conjugate base for that. That means all of the blue protons are staying put. That means the central carbon is going to have a negative charge. And there we go. All right. Now we'll do the opposite one and remove the blue protons, and I'll do that going a different direction. So I'll write minus the blue proton. Oops. And we'll draw the conjugate base for that one. And that means the carbon on the far right-hand side has a negative charge in this one. All right, if we look at both of these, we could say, all right, we've drawn out all possible conjugate bases. Does it matter which of the blue protons I took? No, they're all equivalent to one another. All right, we go down the list and we'd say, all right, is one containing a different charge than the other? No, they're both -1, right? Then we go to atom, we'd say, the negative charge is on a carbon in both of those, so we're tied at the atom level. All right, after that, what's next? Resonance. All right, so let's focus on this one. Is there any resonance that we can draw? Well, let's try, right? Let's assume I try to move this negative charge to be down here and form a new pi bond. Is that okay? No, that carbon already has an octet, right? If we form a triple bond there, that carbon on the left would have 5 bonds. That is not allowed. All right. Conversely, we can say, well, what if we move it that way? Same thing. That carbon would have 5 bonds. So this one has no resonance in the top right-hand corner. Let's try the bottom one and say, all right, what if I move that there? Now that central carbon has 5 bonds. Can we fix it? Yeah, we can break this pi bond and shuttle the negative charge all the way over to the left carbon. So this one has a resonance structure. And we'll draw in all of our color-coded protons, but this time the negative charge is located down there. All right. So really quickly, looking at this, we can say, well, if we remove one of the blue protons, we have a resonance stabilized conjugate base. That's more stable than if we were to remove one of the red protons. Therefore, the blue proton must be more acidic, right? So let's make a note of that. The blue protons must be more acidic since the potential conjugate base is more stable And like we said, this was due to resonance. Does that make sense? It's really easy in this case. We only had 2 potential protons to look at. But let's try one that's a little bit harder. We'll gradually work through. So for this one, I want you to determine where the most acidic protons are on ethanol. And then explain why. Actually, let me color code this. I've got a green proton here. I've got 2 protons coming off the CH2 portion. And I've got 3 of them coming off the CH3 portion, so I'll color code those as red. All right. Which proton type do you think is going to be most acidic? The red protons, blue protons, or green protons? And check with your neighbor and see if you agree. If you agree with your neighbor, give me a thumbs up. If you feel pretty confident, give me a thumbs down. If you're lost, a sideways thumb if you're kind of not sure. I'm not seeing very many thumbs. A few sideways thumbs, a few thumbs up, a few thumbs down. All right, so I'll show you how I would go about doing this. So in the first example, let's just choose a red proton. I'm going to remove that and say, all right, negative charge there. That would be a negative charge on a carbon, right? Okay, let's put that back and say, all right, we know one of the potential options would be to have a negative charge on a carbon. Let's do this one. If we remove that proton, we'd have a negative charge on a carbon. Okay, we'll keep that in mind. Add it back in. And then over here, if we were to remove that proton, we'd have a negative charge on an oxygen. All right, so it looks like we're narrowing it down, right? So one option is to have a negative charge on one of the carbons. The other option is to have a negative charge on the oxygen. Which one is going to be happier? Negative charge on an oxygen or a carbon? Oxygen. Why? Electronegativity. Yep.
It's kind of a little bit off topic, but we should be able to check this using some equivalency between bond length and joules and checking the energy of the...
So you were asking about looking at bond dissociation energy? That's a good question. So bond dissociation energy is different. That's called a homolytic cleavage. So one electron goes to each atom. That's different than plucking in a proton off where both electrons go to one atom. So they're different than one another. But in general, this sort of guideline works really well. Like we said, this one is most acidic since the negative charge would be on the more electronegative atom. So sometimes you can go through these really quickly in your head, no problem, find them pretty quickly. But I'll give you some more challenging ones, because I know everybody likes a challenge. Yep.
Would the blue one then be the second most acidic, because you have resonance structures that you can make off of it?
So the blue one, if you remove one of the blue protons and you have a negative charge there, there's actually no resonance structures that you can do without violating the octet rule on one of those atoms. So there's no resonance in any of these potential conjugate bases. Let's try a harder one though. All right. We've got this hexagon with the nitrogen in there. This nitrogen has a lone pair. And I'm going to narrow down the protons that we're going to look at. We're going to look at this proton over here in blue, these protons down on the bottom in green, and we'll compare these to the red protons up here. Question is, which of these are the most acidic protons and why? So I'll give you a minute to check with your neighbor and see if you agree. All right, so let's go through this together. What I've done is I've just made a skeleton structure just to speed things up as we go through it. So in the first one, we removed one of the red protons. We still have one red proton left over. We still have this blue proton, and we still have both of these green ones. Where's my negative charge supposed to be? Top carbon, that's where we removed a proton, so it's right there. Okay, so that looks pretty good to me for a negative charge and a conjugate base. All right, next one down, we removed the blue proton, so there's nothing coming off of that carbon. And we have 2 green protons right here, 2 red protons here. And where's our negative charge supposed to be? Yeah, the carbon below the nitrogen, the exact spot where we removed the proton, right? So I'll go ahead and draw the conjugate base for that one. All right, and then last but not least, we're going to remove one of the green protons, so we still have our blue proton left. We still have 2 of our red protons, and we still have 1 of our green protons. All right, negative charge is now down here. Like I said before, it doesn't matter how many protons are coming off of a given carbon. Just imagine removing 1 of them. The number of protons doesn't impact anything. Okay, so now that we've got our conjugate bases drawn, we've got to determine which one's more stable. So if we look at all of these, they all have a -1 charge. So we're tied at that charge category. Next, we go to atoms. If we look at the top one, we've got a negative charge on a carbon. Next one, down, we've got a negative charge on a carbon. Bottom one, negative charge on a carbon. We're tied. All right, so after atom, we look at what? Resonance. So let's try to find resonance structures. So for example, I've got this negative charge. Can I form a pi bond right there? Well, if I do that, I have over an octet, but we can fix that. Say, hey, I can move those electrons over there. Oops, no more pi bond, excuse me. So we still have this red proton right here. We still have 2 green protons. We still have this blue proton. But now the negative charge is located over there. Are there any other resonance structures? I don't see any. So we'll go ahead and close this off with brackets. Let's double check the other ones though. All right, the one right below it, we've got a negative charge. Can I move these electrons down here? Nope, otherwise we have a Texas carbon. All right, can I move these electrons right there? Nope. Otherwise, we have a Texas nitrogen, and there's no way of fixing that Texas nitrogen in this situation. So this one has no resonance. So we'll just make a note here, no resonance. All right, and then the bottom one. Let's try this. Say, okay, this negative charge, let's try moving it this way. All right, if we do that, now we have a Texas carbon, that carbon where the blue proton's coming off. Can we fix that though? Sure, why not? Can move the negative charge up to the nitrogen, right? Okay, so let's draw the resonance structure. Everyone's looking at me and scowling. Like, what is going on right now? Why are you doing this to me? I should have just been an English major. But I don't like reading. All right. So here we've got our resonance structure for this one. Looks reasonable to me. We've got a negative charge on the nitrogen. Oop, I'm missing my double bond right there. That's why I keep everybody around. Yep. So, not exactly. You would have to move the electron, then break a pi bond, not both at the same time. I think I'm understanding your question. So your question was, why can't you just kick this up and then kick the pi bond down? Or the lone pair?
The lone pair goes to the blue pi go down, form a pi bond.
Right here? This way then? So if you do that, then the bottom carbon has an octet, or more than an octet. Yeah, so it is tricky. I always recommend drawing all the resonance structures and then cross out the ones that have Texas carbons just to remind yourself these are not valid. All right, so now we're in this tie, right? We know the blue proton's definitely not going to be the most acidic proton. It doesn't have any resonance. But the top one, meaning removal of the red proton and removal of the green proton, both have resonance. So now what do we do?
You suffer.
Well, let's look at the resonance structures, right? And we have to think about them in a bit more detail. In the first one, the negative charge is shared between two carbon atoms, right? The bottom one, the negative charge is shared between a carbon atom and a nitrogen atom. Ooh. Now what do you think is the most stable? Yeah, the carbon-nitrogen one, right? So again, we're kind of defaulting back to that atom rule because we need to look at where that negative charge is located, which atoms it's on. So in this one, we would say, all right, this one is more stable since the negative charge is shared between a carbon and a electronegative nitrogen. So the nitrogen in this case did make the difference. Like I said, this is not intuitive. Oftentimes you have to draw out the conjugate bases step by step, look at the stability by drawing out all the potential resonance structures and so on. That's why I said if you don't understand resonance, it makes a lot of this stuff super challenging, and it kind of limits your ability to analyze acid-base problems. All right, let's do a more challenging one. Yep.
So what if you have a point where one has like 3 resonance forms, but a different one has 2 resonance, but it's on like oxygen has a negative, so like 3 carbons having a negative, or 2 oxygen having a negative.
Okay, so the question was a hypothetical question asking about, all right, what if you're comparing one conjugate base that has 3 resonance structures versus another potential conjugate base that has 2, but the one with 2 resonance structures has delocalization across an electronegative atom where the other one doesn't? It can be hard to tell in that case, and I would refer to a pKa table. Yeah. All right, so let's do a harder one. All right, so for this one, we're going to look at a fused ring system. So it's 2 hexagons that are linked together. I think this might have been off of an old exam. All right, bear with me. All right, we've got a blue proton off this position, green protons coming off that position, and we'll add in 2 red protons over here. Let's determine which of these proton sets is going to be more acidic. Is the red proton going to be most acidic? One of them? Is the blue proton going to be most acidic? Or is one of the green protons going to be the most acidic? All right, let's try to do this as a class just for the sake of time. There's other stuff we need to cover today. All right, so let's imagine we remove a red proton. So I'll just use my eraser here. If we remove that red proton, those electrons must be off of that carbon. Makes sense? All right, let's say we remove the blue proton. That's the middle column. So I'll remove that proton. We would now have a negative charge there. All right, and last but not least, let's imagine removing one of the green protons. So I'll just remove one of those, and we would have a negative charge on that carbon. Make sense? All right, so we go through the cardio rules. It's -1 versus -1 versus -1. We're tied at the charge level, right? Then we go to atoms. And we'd say, all right, negative on a carbon in the first column. In the middle column, negative on a carbon. Last column, negative on a carbon. So we're tied at the atom level. After that, what do we look at? Resonance. So let's focus on column 1, loss of the red proton. And with this one, we can take this negative charge, move it there. However, we would run into a Texas carbon problem. How can we fix that? Yeah, move the pi bond to the oxygen. Okay. So now we can go ahead and say paste. Let's clean this up. So when we do this, we're going to have a red proton there. We're going to have a new pi bond down here. Negative charge is now on this oxygen. All right, are there any other resonance structures that we can draw? I don't think so, without going backwards to our original structure, right? So if we think about loss of a red proton, I'd say we're pretty limited to these two resonance structures, but that's okay. Let's try the blue one. And we can say, okay, with the blue one, are there any resonance structures? Well, let's try. Which way do you want to move the negative charge? Left or right? Left. Okay, so I'll try moving that left. All right, if we do that, we'd have a Texas carbon. So let's try breaking that. Kick it up to the oxygen. Same sort of idea as before, but let's take a look at this structure this time. Okay, so we're going to move this negative charge over here. Whoops. Let me change these to regular electrons. We don't have this blue proton anymore in this structure. We have a pi bond there. We have a pi bond there. All right. I see students draw this a lot as a possible resonance structure. I will say that it's incorrect. Does anybody know why? Give you a hint. Let's zoom in on this a bit more. Right? Think about this carbon right there. What's the hybridization of this carbon? sp. What's the preferred bond angle for an sp hybridized carbon? 180. We're forcing it into about 120. That's not a happy looking bond angle. So I'd say it wants to be 180. Therefore, I'm going to put a little frowny face here and put an X through it and just say this isn't really a valid resonance structure, because in order to accomplish that, we'd be contorting it so far out of VSEPR alignment, it's just really not going to occur. Make sense? All right, now let's do the last one. We can try doing resonance. And if we look at this one, I could say, all right, let's move this over here. Now we have a Texas carbon. That's okay. Move that over there. Oh, another Texas carbon. That's okay. Can move that over there. So let's plug this all in. And we'll draw our new structure. Okay, our new structure has a pi bond right here. We still have one green proton coming off of there. We have a new pi bond over here, and the oxygen has a negative charge, right? All right, we can even go through intermediate structures if we want. So for example, maybe I could kick this electron back down and kick this electron onto that carbon. So we could be super thorough and show all of the possible resonance structures. So let me go ahead and draw this in. Okay, if we do that, this pi bond's still in its same spot, and we have a negative charge right there. All right. So now we've got, I think, all possible conjugate bases with all possible resonance structures drawn. Now, going back to our original question, now that we're exhausted and forgot about it, which proton's more acidic, the red proton, blue proton, or green proton? Green. Why? It's got more resonance structures, and one of its resonance structures allows it to delocalize to an electronegative atom. So not only does it share that negative charge with an electronegative atom, it's distributing that charge across 3 total atoms. Does that make sense? So this one's more stable. Because it has more resonance structures. Oh. All right, so I know this does get pretty tricky. I would encourage you to practice these book problems. They take a while to get good at. They are tedious. Don't be afraid to go slow and make mistakes. All right, there's one last thing we wanted to talk about that you might need for the pod, and that's selecting an appropriate base. If you have that common bases handout that I gave you, you might want to pull that out. But again, I'm going to redraw the generic acid-base reaction and say, all right, we've got a proton of interest that we want to deprotonate. I don't want to deprotonate any other protons. what base might I need to accomplish this? All right. And like I said, you can always think of this being a competition between your original acid and your conjugate acid. And I'm going to phrase this another way. If we want to favor deprotonation, what should be the stronger acid? The acid or the conjugate acid? It's kind of weird to think about, right? We said the stronger acid pushes the equilibrium to the opposite side. We're saying we want to deprotonate our original acid and make A minus. That means our original acid should be the stronger acid, right? It sounds kind of like we're talking in a circle, but it makes sense, right? If we want to favor deprotonation, our original acid must be stronger, i.e. lower pKa, than our conjugate acid. Seems really simple, right? If that acid that we're starting with is stronger, it's going to push the equilibrium towards the product side. Okay, so let's take an example of this. And I'm going to use acetylene. And I'm going to use some generic base. Looks like this. And I want this to ideally be a one-way arrow. Although let's just be consistent with how we've always drawn it and show it equilibrium arrows. And this base is going to come deprotonate it. We really want to deprotonate this and form our acetylide anion. All right, so first thing I would always do is look up the pKa of my acid of interest, or find something that's approximately close to it. So in my pKa table, I'd say, all right, the pKa value I find for this is about 24. What does that tell you about our conjugate base? Should the pKa be higher or lower than 24? Higher than 24. So should be higher than 24 if we want the deprotonation to be favored, right? Okay, so let's find an example of this. Okay, in this first example, we're going to use hydroxide. That's the base you used a lot in Gen Chem. Okay, in this one, same reaction. So now we have our acetylide anion. Like I said, the pKa is 24 for this. Does anybody remember the pKa for water? 15.7. Will this be an appropriate base for deprotonating the acetylide ion? No. So this is a poor base selection. Because this pKa is lower than the original acid. All right, so on the sheet that I gave you, yep.
Can we also look at it, like if we don't do it with pKa, can we do whichever one has the more stable base, or like if the conjugate base or the regular base are more stable?
You can make some educated opinions, but I always like doing pKa's if I can. So what I did for you was I gave you a pKa table, and I gave you bases and their corresponding conjugate acids, right? So in this example, we want our conjugate acid to have a pKa greater than 24, preferably by a few orders of magnitude, right? All right, so if we look at this, what might be a better base to use for this deprotonation? Yeah, we need something greater than 24, so nothing in the left-hand column will work. maybe let's use sodium hydride for this reaction. So in this one, we could say, all right, we take the acetylide anion and we take sodium hydride. You don't even need to show sodium, it's a spectator in this case. So the hydride base will grab this proton, and we could say, all right, in this situation, we made our acetylide ion. What's the conjugate acid going to be? H2, which is pretty convenient as a chemist because H2 is a gas. It's going to bubble out of solution. We said the pKa is going to be 24 here. pKa of hydrogen gas is what? 36. So this would be a much more appropriate base. It's got a significantly higher pKa for the conjugate acid than of the original acid. So that's the second half of the pod that I want you to work on. But what we need to do today is kind of switch gears, and we're going to look at the solvent systems that we're going to be using. So selecting an appropriate solvent for an acid-base reaction. So like I previously said, a solvent normally doesn't participate in the reaction. In a reaction. On rare occasions it does, but what I mean by this is normally we're not going to be making and breaking bonds with our solvent, right? The solvent's just there. That just means that the solvent is the reaction medium. Oftentimes what we do is we choose a solvent that's most appropriate because we need to A, dissolve everything in there, and B, sometimes the solvent stabilizes things and allows the reaction to occur, and we'll see that later in the term. Yeah?
You ever consider the solvent a spectator, or no, because it does not work?
Yeah, so the question was, do you consider solvent a spectator? Yeah, essentially it is a spectator. It's just kind of hanging out, helping to dissolve things for the most part. All right, so let's take a look at an example reaction. All right, in this example reaction, I'm going to have acetone. Acetone only has one type of proton coming off of it, meaning the methyl groups on each side, the CH3 groups. All of those protons are equivalent. I'll just show one side, and I'll say, okay, each of these protons I'll label as red. And if you look this up in a pKa table, the pKa of acetone's protons is about 19, give or take. All right, if we go back and we want to select an appropriate base, maybe I'm going to pick sodium amide, which is NH2 minus. And in this reaction, we could imagine, hey, this base could theoretically grab this proton, clamp down, and we could get a carbon with a negative charge. Is there anything else stabilizing this conjugate base? Resonance, right? So we could draw the resonance structure for this if we wanted to. So maybe I'll do that right below. Say, hey, this does have resonance stabilization. Just to practice, we'll draw this in. And this is a common anion referred to as an enolate. So a resonance stabilized negative charge getting picked up to an oxygen on a carbonyl. All right. And then if we think about this too in terms of our conjugate acid in this case is going to be ammonia. The pKa of this is going to be about 38. So is this deprotonation event going to be favorable? Yes, absolutely. So if we look at this though, we could say, well, we've got a reagent. The reagent and the starting acid are typically put into a solvent anytime you're doing a chemical reaction. So let's pick the universal solvent. And I'll say, all right, let's just run this reaction in water. And I'll even color code this as blue. And we'll just say, what if this is our solvent? All right, so then the question is, will this reaction work? Why? Okay, the pKa of water, in this case it's our solvent, is 15.7. What's the problem then? Water is more acidic than the thing we're trying to deprotonate. It's going to get deprotonated before acetone ever gets protonated. So let's make a note of this. Water, our solvent, is more acidic, therefore it will get deprotonated. Essentially, this acid-base reaction will not occur. So I'll just go ahead and write, this will not occur. Just put a big X through that. All right, so now the question is, all right, we need to pick a solvent that has a higher pKa, right? So if you go ahead and look at that handout that I gave you, I've got a bunch of organic solvents that are commonly used in a lab setting. And I've classified them by a variety of different categories. The first ones are called polar protic. So I've got ethanol, methanol, and water. What do you notice about all of these? They're about the same pKa, and what special intermolecular force do they have? H bonding. Okay, so these can H bond. Okay, polar aprotic. If we look at these ones, they're polar molecules that cannot H bond, right? None of the hydrogens in these polar aprotic molecules are coming off of fluorine, oxygen, or nitrogen, but they're still very polar. And then down on the bottom, we have nonpolar compounds. So not only can they not H-bond, but they have no significant net dipole associated with them. They might have a small net dipole, but nothing on the range of our polar protic or polar aprotic compounds. So sometimes we'll choose different solvents based on whether or not the reaction's favored in solvent that's polar or nonpolar, and we'll talk about that more when we get into reactions in second term. All right. So let's pick a solvent that might work better for this reaction. Okay, so then we could say, well, maybe we're going to run this in, what might work? Acetonitrile. Acetonitrile, sure, why not? We'll say acetonitrile. Okay, so maybe we can just take this whole reaction. I'll use my power of the lasso tool. Copy it down. Cowboy Jeff. You can just copy over your notes. I know. Lasso everything. All right. So let's do acetonitrile. If you think about it too, acetonitrile has how many carbons in it? 1. Somebody was asking me about this. It's important to remember that this spot right there is a carbon, right? So the part where the line meets that triple bond is an assumed carbon, and then out here we have a second carbon. So it's 2 carbons. Another way of drawing this, if you just want to draw out all of your bonds, would be like this, right? So make sure that you are aware with triple bonds that that is present. So let me fix this again and say, all right, this is acetonitrile now. Now this is my solvent for the reaction. We're no longer going to use water. So I'll color code this for my solvent. Come on. Either way, I'll just box it. There we go. So this is my solvent now. What was the pKa of acetonitrile? 25. All right, in this case, the reaction will work. What's going to happen to the solvent in this reaction? It's just going to hang out. It's going to do its own thing, kind of watch the reaction take place, which is good. We don't want our solvent to participate in this reaction, we don't want it to do acid-base chemistry. So we do have to be pretty prudent anytime we're selecting a solvent. Does that make sense? All right. So let's make a note. This reaction is favorable since the solvent won't be deprotonated. Okay, I'll show you another common trick that organic chemists use. And this one's going to be a bit different. We're going to start out with not acetone, but this compound called acetyl-acetone. So it's a diketone, right? Two ketones in one molecule. Where's the most acidic proton going to be? In the middle, right? We saw in our problem of the day that if we deprotonate one of these two protons, we have a structure that is doubly resonance stabilized, right? That's good. All right, so I'm just going to pick a base. I'm going to pick sodium amide again. I'm not going to show my spectator cation, but we can show our arrow pushing, and we can say, all right, I'm going to grab this. Or actually, sorry, I'm going to change this base. We'll make it easier. Let's do hydroxide. I apologize. But same idea, right? Hydroxide, in this case, we can imagine deprotonating one of those. And in this case, we're going to try to find a solvent to put into that blue box. We can show our equilibrium arrows. I'm not going to bother drawing the resonance structures for this one, but you get the idea. And in this case, water is going to be our conjugate acid, and we want our solvent to basically just be hanging out during the reaction. All right, first thing I would always do is double check that my base was good enough. So if I go to the pKa table and look for this diketone, let's go ahead and do that. I've got a ketone here. If you notice on top of the ketone side, it has a little X group dangling off. It's saying what's in that X position. So the first option is, well, what if it's just a hydrogen? That's not what we're looking at. What if it's a phenyl group? Not looking at that. What if it's a sulfur? Not looking at that. All right, what if it's a COCH3? In that case, that's exactly what we're looking for. So in this case, we're looking at something that has a pKa of 9, right? So let's go ahead and plug that in and say pKa of this is going to be about 9. All right, if we think about our conjugate acid over here, what's the pKa? pKa is 15. 15.7 if you want to be precise. All right, looks like it's checking out, right? We're over 5 orders of magnitude difference, so that's definitely favorable. Now we've got to pick a solvent. Should our solvent pKa be higher or lower than 9? Higher. Okay. But what if I just want to make my life easy and I don't want to throw anything new in this reaction? What if I just run this reaction in water? Water is cheap, cheapest solvent available to us. Will this work? Well, let's think about it, right? pKa of this is 15.7. Is our solvent more acidic than our starting acid? No, it doesn't matter. Our base is still going to go after the most acidic proton, which is right in the middle there, like we're showing with our arrows. So in this case, water is not only our solvent, but it's our conjugate acid. As a chemist, I like this. This is fewer steps of purifying my product. I don't have to get rid of my solvent because it's the same as my conjugate acid. So in this case, oftentimes we choose a solvent that is the same as our conjugate acid. Does that make sense? It just makes life a lot easier for chemists. It does look a little bit weird when you're looking at it. So let's say trick. Chemists often choose a solvent that is the same as the conjugate acid. And just to clarify, I'll write that this is my solvent for the reaction. Does that make sense? Yeah.
So would that mess with equilibrium at all, or no, because the PKs are far enough apart that it's essentially just going to drive it forward?
Yeah, so the question was about whether or not water will mess with the equilibrium. Not really, because we're greater than 5 pKa difference, or 5 pKa units apart, it's going to favor the product side no matter what. Yeah. We'll talk more about kinetics later. Basicity, we're looking at thermodynamics, not reaction rate necessarily. That's something entirely different, but we'll talk about that later. Yeah.
So when you're treating the solvent, it has to be greater than the acid, but then does it have to be less than like the pKa that conjugate acid?
So the question was, your solvent pKa needs to be higher than your starting acid for sure. But what about its relationship to the conjugate acid? It doesn't matter as much. You just want to make sure that it's not getting deprotonated before your acid is. Yeah.